So good evening. I'd like to welcome everyone to the Jeffrey B. Graham Perspectives on Ocean Science lecture series. My name is Harry Helling. I'm the executive director here at the Birch Aquarium at Scripps, and it is my great pleasure to introduce our speaker this evening, Dr. Grant Deane. Grant is a research oceanographer with the Marine Physical Laboratory here at Scripps Institution of Oceanography. Originally from New Zealand, Grant joined the MPL in 1991 as a Mellon Fellow from the Mathematical Institute at the University of Oxford in England. Grant is a Fellow of the Acoustic Society of America and plays a prominent role in applying science of underwater acoustics to the study of oceans. In brief, Grant, who I know personally, has a deep appetite and an immense curiosity for how the world works. He's unique in that he studies just about everything happening in the world's oceans, from the impact of Navy sonar on humpback whales to the health of coral reefs, to changes in water temperatures, to the sounds of glaciers calving and melting into the ocean, to learn about climate change and rising sea levels. Most recently, he's leading an effort to construct a new multi-million-dollar NSF-funded facility at Scripps Hydraulics Lab called the H-Lab, and it's a 100-foot-long flume that allow researchers to take a piece of the ocean and simulate the biology and the chemistry, the waves, the wind, the whole top layer of the ocean, from polar conditions to tropical conditions. That new facility is called SOARS, stands for Scripps Ocean Atmosphere Research Simulator. It will be the largest simulator of its sort in the entire world, and we have today one of the people who conceptualized that and is building something that's going to change. Well, I would say, finally, Grant is one of the researchers here at Scripps who selflessly dedicates his time to education outreach. We are so fortunate to have scientists like Grant who are willing to share their science with all of us, all of you, all of our students. Please join me in welcoming Grant for his talk entitled Bubble, Bubble, Toil and Trouble.
Well, thank you for that introduction, Harry. And it's delightful to see you all this evening, if I could see you. Yes, there you are. And I hope to bring you into the world, the fun world, the interesting world, the magical world of bubbles this evening. And yes, I actually say that with a serious tone in my voice. I am a grown-up scientist, and I really am going to talk to you about bubbles. And I hope in the next 30 minutes, you will come to appreciate some of the things that I appreciate about these wonderful things that we have in our lives, bubbles, and why they're important to me as a scientist at Scripps, and why I think it's important that we study them. So I would like to take a moment and ask Dr. Stokes to stand up, please. He's right there. Thank you. Dr. Stokes. My great friend and colleague, we've been working on these topics together for over a quarter of a century. And I happen to be the one up here delivering the lecture today, but it could equally well be him. I'd also like to acknowledge Scripps, this wonderful institution that supports the work that we do. We certainly couldn't be doing it if we weren't here, and if it wasn't for Scripps. The National Science Foundation, and the U.S. Navy Office of Naval Research, because it turns out that they have an interest in bubbles also. I don't normally dedicate my talks, but this particular talk is dedicated to my dear wife, Noelle. It happens to be her birthday today. And here she is, listening to me talk on about, yes, bubbles once again. So thank you, sweetheart. All right, so let me say a little bit about bubbles in general. Bubbles are everywhere. I enjoyed a glass of champagne earlier this evening with the opening of the wonderful new exhibit. It was a pre-opening, it's not the full opening. It was a preview for an exhibit. And we had bubbles in the champagne, and carbonated beverages are part of our life. And I'll talk a little bit about more why there are actually scientific reasons why carbonated beverages are carbonated but nevertheless, it's a common everyday occurrence where we find bubbles. And then this is a representation of foam, which is industrial bubbles, if you like. Bubbles are used for wastewater plant treatment, for industrial processes, for bubble wrap. Where would we be without bubble wrap? Bubbles are used for all kinds of industrial processes, and they're very important in the industrial world. And then, of course, we have soap bubbles, everybody's favorite. Who doesn't love a soap bubble? And if we think about what a bubble really is, a bubble is an interface or a boundary between two different media. Here, the boundary of this bubble is literally made up of water and soap, whereas a bubble in the ocean is air and water. But it has a sense of a boundary. And I think everybody could realize that about bubbles. That's something that everybody can understand. And the other thing that everybody knows about bubbles already is that they're transitory. Bubbles come and go. We're in an economic bubble, or I'm going to burst your bubble, or whatever it is. Bubbles aren't expected to last. They're ephemeral. And that's part of their delight and their charm, that they don't last, they don't survive. And it turns out that bubbles do very interesting things when they disappear, and they do very interesting things when they're first made. And I'll be talking about that a little bit more in the talk once we get there. But I thought I would entertain you with a little bit of, sorry, I can't even do it with a straight face. No, I'm not going to bore you with mathematics. But I do have a reason for putting this up here. I mean, my training is as a mathematician. And there is actually this elegant, delightful world of the mathematics of bubbles. And I'm not kidding you, there are people who study the theory and mathematics of bubbles for good reason. There is an equation that I find to be beautiful, really, is the only way I could describe it. Yes, I'll stand by that. That is a beautiful nonlinear differential equation that describes the dynamics of bubbles. But that is all I'm going to say about that equation. And I promise there are no more equations in this talk. That's the only one. But I really did feel compelled to put that up there. All right. This is the star of tonight's talk. Bubbles in the ocean. And here you see a cloud of bubbles in the ocean. They're out there. They're doing things. They're important. And I'm going to focus the remainder of my remarks this evening on bubbles in the ocean. And where do bubbles in the ocean come from? Well, they come from all different kinds of places, it turns out. But the ones that I want to talk to you about are the bubbles that are made by breaking waves. So, in fact, just over here you can see the bit of crest of this wave that's breaking on the open ocean. This is all the air and foam that's left behind this big breaking wave on the ocean. This white milky stuff is a swarm of bubbles in the water, and when it rises to the surface it leaves this patchy foam, which is a collection of bubbles that have come up to the top. And if you look at these clouds of bubbles from underneath, they look like rain clouds, like storm clouds, because they're reflecting all the light back out at you. So underneath, they're dark. And this is where they come from, breaking waves on the ocean. And if you've ever been out at sea in brisk weather, and I do go out to sea in brisk weather, I can't say I find it a delightful experience, actually. There's a unit of seasickness in my lab that's called the Deane, but it is much too large for practical use. So you'll be familiar with whitecaps, and whitecaps are the waves driven by the wind that overturn and break and entrain these clouds of bubbles. So on to the bubbles themselves. A bubble's life. Well, it turns out that bubbles do very interesting things when they're first made, and interesting things when they die, and I'm going to tell you about that. So I'm going to tell you a little bit about that, and then I'm going to tell you why I think that is important, and then I'll wrap up. That'll be the very end. So I've got two interesting things to tell you about bubbles. One happens when they're first made. and one happens when they burst at the end. So, the birth of bubbles. Why is that special? Well, it turns out that all the musical sounds of running water come from bubbles. And it's curious that most people don't know that. Perhaps one of the quintessential human experiences is listening to running water. What person on the planet wouldn't recognize a running stream or a tinkling fountain or just the sounds of a live running water? Something that everybody recognizes. And yet those sounds come from bubbles. And being a scientist, I thought I would prove it, just in case somebody out there doesn't believe me. So here I have a glass, I have water. I'm going to tip it from one into the other. Everybody heard that, yes? Yeah, very commonplace sound. Everybody, you could have your eyes closed and you'd know what I did. But if I pour it so that there's no air, completely silent. The sound of a fountain. The sound of breaking waves on the seashore. These soothing, wonderful sounds are made by bubbles, entrained by the droplets as they fall on the water, or the overturning, crashing wave as it reaches the shore. So, some of you may have already known that about bubbles, but even if you did, you might not know this, that in the Arctic, glacier ice is full of bubbles. It turns out that as the snow comes down and falls on the top of a glacier, over time it becomes compacted and it traps layers of air. And as more and more snow falls over hundreds of years, at the base of what's called the firn layer, all that air closes off and becomes discrete bubbles in the ice. And then more ice builds on top of it, and more ice builds on top of it. And it's all under tremendous pressure. And it sits there for hundreds of years until finally that ice breaks off the end of the glacier into the ocean, and it melts, and that air is released as a big explosion into the water. And I'm going to show you, I'm going to let you hear what that sounds like, probably more than once. So those pops and crackles are the sound of the air exploding out of the glacier ice. In fact, back in the 1970s, you could buy the stuff. They brought it down and sold it in I was too young for this, but they sold it in the grocery stores, and they called it Seltzyburger. And you would put it in your drink. And that's me up there. So one of the things I do is I go up and I study this. And I go to the Polish Polar Station. And on Friday night, it's possible that we may occasionally have a party on a Friday night. And I became the resident expert on the correct glacier ice to use in your beverage. It turns out that the best ice has the smallest, most compressed bubbles. So I made myself very useful up there. And here I have a picture of what this ice looks like. Clouds and clouds of ancient bubbles. Of course, some of my colleagues here at Scripps take sections of ice like this from the Antarctic, and they extract the air out of the bubbles, and they look at ancient atmospheres that way. I don't do that. I just listen to what happens as these bubbles explode into the water. I'm a terrible disappointment to my colleagues. And just for your amusement, here's some high-speed video footage of, this is very much slowed down or speeded up, however you want to think about it. Each image in this video is 1/2000th of a second. So the whole thing is over in an instant. You can see the little cap of ice that fragmented off that bubble. And so at the front of a glacier, there are millions upon millions of these events happening all at the same time, making this loud underwater sound in the waters around the glacier. So I thought I would explain to you, for interest's sake, why the bubbles do that. Why do they make a sound when they're first formed? Why don't they make sounds all the time? And it turns out that the reason they make these sounds when they're first formed is because they're so not spherical. They're so distorted when you make them. And you might amuse yourself for a few minutes thinking about, well, can I take a bubble and turn it into two smaller bubbles without stretching it out somehow? And if you can think of a way of doing that, I would love to talk to you after the talk. I don't think that's possible. So the bubbles are always distorted. This is a bubble fragmenting in strong fluid flow. This is a bubble formed by a drop of water falling down on the surface of the ocean. And this is a bubble released from a nozzle. There's a nozzle right here, and we're letting gas out of it. And you can see right at the moment when this neck pinches off from the nozzle, there are forces called Laplace pressures that arise from surface tension on the bubble. It goes back to that equation that I promised you I wouldn't show you again. And essentially what happens is this neck shoots up into the bubble, and it's almost as though you had a little bell and you struck it with a hammer. That's what that neck does, and it makes the bubble ring like a bell, and that's why you get these musical tones from the bubbles. That is the mechanism that gives rise to these delightful sounds that we enjoy so much from water. Okay, well, that's an interesting fact about bubbles. But why go to the trouble and effort of studying them just because they make interesting sounds? And the scientific application here is not to understand why the bubbles make sound, but it's to use the sound to measure how many bubbles there are. So if we go out to sea in a storm, and here you're looking at an experiment that Dale and I did back in 2000 from a very interesting vessel called the research platform FLIP, which is this long cylinder that has no engine, and it gets drawn out into the ocean, and then you flood it. Yes, you take a perfectly serviceable working vehicle and you flood it, and it flips. So now the long cylinder's in the water this way, and it sits there very stably, and you put out booms, and you put your instruments in the water and make measurements that way. And the time when the most interesting bubbles are around is when there's a storm. And that's when it's most difficult to get your equipment to function properly in the water. So FLIP is very useful in that regard. It just sits there while the storm goes by and we can make our measurements. So I'm going to show you this video footage now of the data that we took. This is under the water. This is looking down from above. And you'll see a breaking wave come across and all the bubbles underneath. And there they all are. So we deploy underwater microphones with these kinds of experiments, and we record the sounds that the bubbles make, and we can use those sounds to count how many bubbles there are in a breaking event like that. So that's the scientific connection. So I promised to tell you something a little bit about what happens when bubbles die, the death of a bubble. So you now know that bubbles make these nice, joyful sounds when they're first created. What happens when they burst? Well, it turns out that some very interesting things happen when they burst. And one of the things that happens is that the film of the bubble, this is a bubble, imagine this is a bubble floating on the surface of the ocean, made by a breaking wave, and it forms a hole in the side, and then the same forces that make the bubbles ring actually are the forces that make this film retract. And the material collects along the rim, and it forms these ligatures that fragment into these tiny, tiny drops. And there's another mechanism that forms drops too, actually. These are called film drops, I guess because it's a film that makes them. And then these are called jet drops. When this film collapses, there's a wave that propagates from the rim of the bubble right down to the center of it. And then it forms a jet that shoots out, and that jet breaks up into little droplets. And in fact, if you took a glass of seltzer water or soda or whatever, and you've got bubbles bursting on the top, if you just shine a light and look sideways, you'll see all these droplets coming up and out. Or if you do what I do, you'll just put your face in the glass and you'll feel the little droplets coming up on your face. Yeah, I do that. My poor wife. So there are these jet drops that come up as well. And we call these droplets sea spray aerosol. I think when most people hear the term aerosol, you might think of hairspray or some other thing that comes out of a can. And that definitely is aerosol. But in the scientific parlance, aerosol is any solid, small particulate matrix within a gaseous body. So if I take this cap and I turn it into tiny droplets and I eject that up into the air, that's also a kind of aerosol. Now, and this is scientifically interesting because so now you know that we're interested in the sounds of bubbles because we want to count them, but I haven't told you why we want to count them. And I've told you that when these bubbles reach the surface, they break into these tiny droplets and they form aerosols, but I haven't told you why we care about that either. So now we get to the part of the talk where I'm going to bring it together and tell you why we care about those things. So just a few facts about our planet. To put things into perspective, to put bubbles into some kind of global perspective. The total area of the Earth is 510 million square kilometers. That is huge. That is the size of the planet. That is the planet. That is the whole planet. That is planetary scale size right there. 510 million square kilometers is the size of our planet. Now, the size of the oceans is 360 million square kilometers. That's 71% of our planet is ocean. So it turns out that what we are standing on is not what's common. What's common is ocean surface. There's more of that than anything else. So this special boundary, where the atmosphere hits the ocean, that very special boundary is the most common boundary that you will find on our planet. And the exchanges that occur across that boundary control weather and climate. If you took all the heat capacity of the atmosphere, if you wanted to heat the entire atmosphere up 1 degree, that's like heating up the top 10 meters of the ocean 1 degree. And the ocean, the average ocean depth is 2,000 meters. So the ocean exerts a huge influence on weather and climate. Another thing you might not have thought about, we live at about the same latitude as Florida, but we do not have Florida's weather. And if anybody's here from Florida, I apologize, but I prefer San Diego weather. Why is it so different? Well, in Florida, you have the Gulf Stream carrying heat and salt in the ocean north. And here we have the California current, which carrying cool water down our coast from north to the south. And that makes the difference to our climate. The California current is one of the important reasons why we don't have a climate that's more like Florida. Now, I hasten to add, I'm not an expert on regional climate. So, and if someone from Scripps was here, they may correct me. But the ocean currents do play a very important role in determining the climate of where we live. And we've just determined that the oceans are the most common thing. The air-sea boundary is the most common thing. So now, how much of the ocean is breaking at any given instant? Well, that depends on the wind. So if the wind is blowing very strong, you get more breaking waves, and if the wind is not blowing at all, you don't. Well, it turns out that global average wind speeds are between 6 to 7 meters per second. That's about 15 miles per hour. And at that wind speed, this is how much of the ocean is breaking. 250,000 square kilometers. That's the size of Wyoming. That's a lot of ocean breaking. And I made an estimate of the number of bubbles made by those breaking waves. It's 3 by 10 to the 18. That is 3 billion billions. So take a billion and then take 2.9999 billion more of them, and that's how many bubbles you have at any given moment in the ocean. And when you've got that much of anything on the planet, well, certainly with bubbles, it starts to add up. And certainly the effect of these bubbles does add up. And so continuing on this, putting it into perspective, I have here a simulation for you made by some NASA scientists of a model called GEOS 5. And what these scientists have done is simulated the production of aerosol across the planet for a year. Now, not all these aerosols come from the ocean. Aerosols come from forests, and they come from deserts, and they come from biomass burning, and they come from a wide variety of different sources. The blue ones that you see over the oceans are sea spray. That is the sea spray aerosol. And let me play this animation for you. It's really quite spectacular. So these are hurricanes here. This is all sea spray up around Greenland. Dust coming off Africa. This white stuff, that's sulfates. That comes from industrial activity. So you'll see these are centered on, these are anthropogenic sources, so they're centered on industrial activity in cities. And here more ocean sea spray. Indonesia's really going for it here. And it's most intense here because the strong winds and the hurricanes produce a lot of sea spray. And I think this thing finishes with a grand view over the Antarctic. It's kind of mesmerizing, isn't it? In the Pacific Ocean, there are very few other sources of sea spray. So a lot of the aerosol that's in the atmosphere here comes from the ocean, comes from these breaking waves. Okay, so why do we care about the aerosol? Clearly there's a lot of it and it occurs on a global scale. Well, it turns out that at the center of every cloud drop is one of these little particles. Cloud drops form on the aerosols. And ice, turns out, also is a very important thing in the atmosphere. Ice changes the Earth's radiation balance and the radiative properties of the atmosphere. And ice also forms on these particles. And if we ever want to model the Earth's climate, we have to model the clouds correctly and the ice correctly. And if we want to model those correctly, then we have to model the sea spray correctly. And it turns out to be a very challenging problem. And here I've got the connection here between clouds, and here the sea spray is so numerous and so large, you can see it coming off this breaking surf here. And this is the connection between the ocean, the waves and the bubbles connect the oceans to the clouds and the ice in the atmosphere. And I'd like to put in a little plug here for the Center for Aerosol Impacts on Chemistry and the Environment. It's a very large center here at Scripps, proposed and run by a professor here, Kim Prather, that studies this problem, this global problem of how can we model and understand these aerosols and what they do to the planet. Well, clearly, the bubbles, which are the origin of all these aerosols, play a vital role in understanding that problem. And that's one of the reasons, one of the really strong motivations for us to go out and understand them and measure them. We need to count the bubbles, we need to know how big they are, we need to know what organic matter they scavenge out of the ocean and transport up into these clouds so that we can do a better job of climate model simulation. In fact, we are so interested in that problem that we are going to spend $4 million to build an ocean simulator in the hydraulics laboratory. This is the machine that Harry mentioned earlier. The National Science Foundation is funding 2/3 of it, and Scripps is funding the other third. And thank you so much, Margaret. It's very much appreciated. So this thing is 100 feet long. It's about 8 feet by 8 feet square. There's a person, and there's another person to give you the sense of the scale of it. And in this machine, we will simulate the current and future ocean. We will control the composition of the atmosphere in this thing, and we'll put more carbon dioxide in and see what that does to the organisms and the sea spray that comes off this thing. We will change its temperature. We can cool it down. We can heat it up, and it will be built from all non-toxic material. We're partnering with the Stephen Birch Aquarium. They're going to make sure that we don't use any toxic materials, so we can use it as a giant mesocosm. And we'll grow the biological organisms in here that are the engine for the chemistry that ends up in the aerosols that controls their climate-relevant properties. So, just because I didn't want Shakespeare really angry at me, I thought I would correct it. Double, double, toil and trouble. I think you can get a sense of the time and effort we're putting into studying this problem. It's not just a lot of money, it's a career, or multiple careers. There are those of us who think bubbles are delightful, but they're also very serious business. And we toil over them, and we try not to cause too much trouble as we're doing it. And that's all I had to tell you about bubbles. That's the end of the talk.
In the surf spray zone, you can see water droplets on the surface of the ocean. They are very small, of a uniform size, under a millimeter, seem to last about 10 seconds. There seem to be more of them when the atmosphere is dry. I've observed this, but maybe you can enlighten me as to what is going on with them.
Okay, so you're talking about the water droplets.
They do not appear to be bubbles. They appear to be droplets. They're very small.
Yes, yeah.
But why don't they immediately merge with the ocean? They instead seem to sit on the surface of the...
Oh, right. That's an interesting problem, actually. Oh, and by the way, I don't know if any of you know the program Two Scientists Walk Into a Bar, but you're allowed to ask anything you want. So, and that would be very nice. So if you just have, and if I don't know, I'll just say I don't know. So any questions at all are welcome. So, Yes, the bubbles, those droplets have a little film on them, on the exterior, and that's what stops the immediate coalescence with the water underneath. Some of them will coalesce right away, but you might also observe it sometimes not in the kitchen or in the sink. You get these tiny droplets form that roll around on the surface. That's what you're referring to, yes? Yes. What stabilizes them is a layer of organics on the droplet. And interestingly, it turns out that the aerosol droplets, which are much too small to be seen by the human eye, also have a coating of organic matter on them. And that coating alters their water uptake in the atmosphere, their hygroscopicity, and that alters whether or not they make cloud drops or raindrops or not. So the question that you asked and the properties, the climate relevant properties of sea spray are related. Well, thank you for that interesting question.
Thank you. This is quite fascinating. I wonder if you're familiar with the work of Professor Gerald Pollack at the University of Washington, bioengineering, because exclusion zone water, where he talks about the fourth dimension of water, you can watch YouTube videos and about it. It's fascinating. But when you talk about biofilms, that's exactly what he talks about in the exclusion zone. And I wonder if you're at all familiar with that or have included any of his work in what you're doing?
No, I'm not, which is perhaps a disappointment. I should be. One of the great discoveries we've made in the last 15 years in the subject area, and it really is a great discovery, is that at the surface of the ocean, you cannot discount the physics or the chemistry or the biology. The ocean itself and the system of the ocean and the atmosphere doesn't discriminate. We discriminate. We have oceanographers and we have chemists and we have biologists. But the ocean doesn't care. It just does its thing. And it turns out that the chemistry is driven by the biology, and the chemistry then controls the climate relevant properties of the sea spray that are created by the physics. And that is why in the 21st century, we must bring together scientists from different disciplines to study these multidisciplinary problems. This is my great hope for SOARS, that it will be a machine that will attract people from different disciplines. It will bring us together, and we will, as a grand challenge, start to tackle these problems, which are truly interrelated and interconnected. We can no longer afford to parcel off a piece of the system and say, I will study only this, because it is all connected. So perhaps after the talk, you can enlighten me more about that work. Thank you.
What role does surface tension have to those tiny bubbles that are the droplets of water, I should say, when they're scattering around on the surface?
What is the role of surface tension? Actually, that's a very interesting question. Surface tension, for those of you who aren't familiar with it, think of a balloon. A balloon is elastic, and to blow it up, you have to stretch the membrane. So liquids have this property of, if you want to increase their surface area, you have to put energy in to increase the surface area. And that property is called surface tension. So that is why we don't find, in general, rectangular prisms of water. We tend to find spheres of water because they want to minimize their surface area. And the smaller the droplet is, the more important the surface tension is in driving its shape and its properties. So for droplets that are a centimeter scale and so on, you'll find them all different shapes and sizes and they break up. But once you get smaller than a fraction of a millimeter, surface tension becomes extremely important. And that's also true for bubbles, by the way, as well. And then a number of the processes that I was telling you about the bubbles ringing, and the formation of the bubbles themselves and their destruction. Surface tension is critical to all of that. The kicker here is that surface tension is altered by the chemistry. So there's a connection between the physical properties of the system and the chemical properties of it. The chemistry drives the surface tension, which controls the physical properties.
If you put anything in seawater, it rapidly becomes coated by a organic film that changes with time, both inorganically and organically. its chemistry will change. In your SOARS experiment, and that will also include the surfaces of bubbles. It's the surface. How in your SOARS facility are you going to hope to mimic an ever-changing system that is probably nothing like the real ocean?
Ah, okay. Tough audience tonight. All right. No, that of course is a very insightful question, and I could talk at length about it, but I promise you I will try not to. The biological systems that we mimic in our mesocosms aren't entirely unpredictable. If they were, there would be no point in growing mesocosms. Or indeed, the marine aquaria that are next door would randomly change state from one day to the next. But that is not what we observe. If you take a tank of seawater and you spike it with nutrients and you shine light on it, there is a competition between the microorganisms, the phytoplankton, in terms of their explosive growth. And as you point out, you won't always get the same explosive growth of the same organisms, but you will always get an explosive growth unless you have some toxicity in the water that is undesirable. Even though we don't know precisely which species of phytoplankton may dominate, we can, if we wish, control that by introducing a pre-growing culture into our system. So if we wish, we can add sterile seawater and spike it with known organisms and therefore control that system. If we want a more natural mimic for the ocean, which as you quite correctly point out, we want to be as close to the ocean as possible, we can let those natural organisms grow. We might not know exactly what phytoplankton they are, but we do know that they're phytoplankton. As those phytoplankton grow exponentially, eventually they consume all the nutrients and the population starts to crash. At that point, the marine bacteria start to grow. So the phytoplankton grow and they start to crash, and then the marine bacteria start to grow. And then the viruses start to grow. And that progression of blooms is not precise, but it is representative of the ocean, and it is something that we can control. The biggest thing that we do that the ocean doesn't often do is we spike it with nutrients. Blooms in the ocean are a much more gentle evolving process. In terms of the randomness of the chemistry, it's true that I suspect that there are global and regional differences in what are called the bioexudates and the bacterial films and mats that are produced by the picoplankton. And you seem to be very knowledgeable about planktonic organisms. You may know about these transparent exopolymers that are produced as bioexudates. Sorry, I'm talking Gabonese. These organisms, bacteria are fascinating. Their stomachs are on the outside. The marine bacteria are too small to ingest anything, but they need to eat. So they put all their digestive enzymes on the outside, and then they digest whatever's out there, and then they suck it across their membranes. And then whole colonies of bacteria form bioexudates and bacterial mats. And the real authority on the subject is not me. It's a professor called Professor Farouk Azam, and he understands this topic very well. But the bacterial mats are always present when you have bacteria. So there is some kind of reproducibility to what we do. Part of the reason we're building SOARS is so that we can mimic equatorial oceans and Arctic oceans and Antarctic oceans. We'll have heat exchanges and we'll control the water temperature. So we can grow different organisms, and we can spike the system as necessary. Please also bear in mind that we aren't trying to achieve complete control over everything We can do that in very small scale tank experiments. We could get complete control. We're trying to give up control to some extent with something of the scale of SOARS so that we can bridge the very controlled desktop experiments and the completely uncontrolled environment that the ocean presents. And it's not just that we can't turn our knobs and dials. It's very difficult working in storms, and you go up to the Arctic and polar bears want to come and have a go at you. You know, it's like, look, there are hazards out there, I can tell you. So we're trying to find some middle ground here. Whether or not we achieve that, we will have to wait and see. I'm optimistic that we can. Thank you for that interesting question.
I just had two questions. One was, in the last 20 years with the scientific instruments you have you been able to notice we've been producing less bubbles than, or any major patterns? And the second part of the question is, what does 1 degree or 2 degrees of heat to the Earth, how does that affect what happens?
Okay, so two parts. For the first part, did you say mussels?
Bubbles. I'm talking about bubbles.
Oh, bubbles.
I'm thinking
Okay.
you have all those scientific instruments.
Right,
You can
right.
tell how much aerosol is being produced, whether it's less or more, or if you're even able to measure it, if you're able to tell the difference between 2000 and 2015. Is there any difference, or is there a way to measure that?
If such historical measurements have been made, I'm not aware of them. I can tell you in general terms that a warmer world has more energy in the weather system, which is an interesting concept. I mean, you know, you can't look at any piece of weather and say that's climate. That's not what climate is. Climate is the context within which weather occurs. There are warm days in Minnesota, and we get frosts out in Poway. But our climate is warm. So in a warm climate, as climate warms, and 2 degrees across the planet is an average increase in climate. But not everywhere will get warmer, by the way. As you move the jet stream around from northern latitudes, as you change precipitation patterns, and as you change the climate system, not everywhere will get warmer, not everywhere will get less rain or more rain. But on average, there is certainly more energy in the system. So we can expect more extreme events. We can expect a greater propensity towards hurricanes, a greater propensity towards heat waves. In California, we can expect a greater propensity for forest fires as precipitation decreases on average, over time, if you took an average over 10 to 20 years, which is what you must do if you want to measure climate. So in a system with more energy, I will expect more bubbles, more wind, more waves, more bubbles. But I certainly wouldn't claim we've measured that. Yes, that's what I would project.
So we have time for one more question.
All right, this is not a question, actually. This is a comment in the spirit of two scientists walk into a bar. I do want to say, finally, after all of these years, I understand how Aquaman survives. Thank you very much.
Excellent. Thank you. Thank you, everybody, for coming.